specifically about sampling distributions of a sample mean. So here is a population distribution of the number of basketball games attended by members of some population. So this distribution is very skewed. Most people attend 0 to 10 basketball games. We got a few people that attend to 20, and then very small numbers of people who attend more than 20, including some outliers over here that attend 60 to 70 games. So, very right-skewed data. Now, let's look at the sampling distribution for the sample mean when a sample of size n equals 10 is selected. So, if we randomly sample 10 people from this population, and we calculate the average number of games that they attend, this is what our sampling distribution looks like. And it's skewed, it's still right skewed, but it's not as right skewed. So, each observation in the sampling distribution represents the mean of one sample of 10 people. So this, right here, is one sample of 10 people with a mean of, it looks like 16 or 17. Is the variability of the sampling distribution smaller or larger than the variability of the population distribution? Well, the population distribution had a range that went up to 70, from 0 to 70, so a range of 70. Here, the range is like 16. But the standard deviation is also going to be smaller. And if we could put this on the same scale, we would see that these are closer together, right? Sample means will vary less than individual observations. Because when you take a sample and you calculate the mean, those higher values and those lower values will balance out and give you a mean closer to the population mean. All right. Now, compare the sampling distribution of the mean for a sample of size 10 versus a sample of size 30. Right? So here, notice that the scales are different, right? This goes up to 16, this only goes up to 10. So the sample of sample size 30 has a smaller, less variation. Less variation. Right? Or smaller standard deviation. We haven't actually calculated the standard deviation, although we could, but right, it's going to be more centered around the mean. It's going to have a smaller standard deviation. The mean of the distribution is still right around 5. Right? The mean still right around 5 here. Here-ish. Right? So the center doesn't change. The standard deviation, the variability gets smaller, and the distribution becomes less skewed. It becomes a little bit more normal looking. Here is one of samples of n equals 70. Again, notice the scale. We have a lot less variability. The mean is still about 5, between 5 and 6. And now it looks basically normal. So, as our n gets bigger, our variability gets smaller, right? Smaller standard deviation and more symmetric or normal shape. So this is the distribution for the population with a mean of 10 and a standard deviation of 7. So which plot is going to go with a single random sample of 100 observations from this population, a distribution of 100 sample means from random samples with size 7, or a distribution of 100 sample means from random samples with size 49. Right? So a single random sample of 100 observations should have approximately the same distribution as the population. Right? So this goes from 0 to 35. This goes from 0 to, you've got a few outliers here at 50, but about 0 to 40. And you've got the same skew where it's pretty strongly skewed right. The sample of 100 sample means from samples of size 7 still has the mean right about 10, but it's less skewed. It's starting to look a little bit more normal, and it has a smaller standard deviation. It's got a smaller spread. Plot C has the smallest spread and the most normal looking distribution, so that's going to have the larger sample size. The central limit theorem is the most fundamental / famous theorem in statistics. It is very, 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 very important. We could get super technical about the central limit theorem, but let's not. The gist of it is, as the sample size n gets larger, the distribution of the sample mean becomes more normal, no matter what the distribution of the population looks like. For this, we have to assume that we're taking a random sample from a large population with a fixed mean and standard deviation. If you want to play with this simulator here, you can do that. I did a couple of them and made GIFs of them. So here, this is taking samples from a normal population. So here, the parent population is normal. I'm taking samples of n equals 5, and my population looked, or my sampling distribution was looking pretty normal. Here, change the population to a uniform distribution, and I still get a largely pretty normal sampling distribution. Here, take a distribution that's skewed right, sample size n equals 5, and I look at my sampling distribution, and my sampling distribution a little bit skewed, not quite normal, but still pretty normal. If I change my n to size 25, my sampling distribution for the normal distribution still looks normal, but it has a smaller spread. For the uniform distribution, also looks normal, and again has a smaller spread than it did before. For the skewed distribution, again, this is me just making it a little more skewed, but my sampling distribution now looks pretty close to normal, right? And has a much smaller spread. So smaller spread, but also look how much closer this is to normal than the other one. Here, going from the skewed distribution taking large numbers of samples. And as I increase the n, watch how it gets more and more normal. And also how the variability decreases. Right? Here, we have we have a much wider spread, and we're not very close to being normal. By increasing from n equals 2 to n equals 5, smaller spread, much closer to normal. Increase that up to 25, much smaller spread, and very close to normal. So, things that we have to check for the central limit theorem to apply. Our sample values have to be independent. If we're sampling without replacement, we can treat observations as independent if the sample size is less than 10% of the population. So our check for independence is usually going to be, is the sample size less than 10% of the population? Or is the population more than 10 times the sample size? Or would it be reasonable to assume the population is more than 10 times the sample size? And our n has to be sufficiently large. How large is sufficiently large? If the population distribution is approximately normal, the sampling distribution will be normal for any n. So we don't have to check the size of n if our population distribution is approximately normal. We don't know often the shape of our population distribution, because if we knew what the population looked like, we wouldn't be doing statistics. So if we know that it's not normal, or we don't know that it is normal, we can still assume that the sampling distribution will be approximately normal for n greater than or equal to 30. That's our rule of thumb here. So, important facts about the distribution of a sample mean x bar. The mean of a sample mean is mu x bar, and that's equal to mu, right? So the mean of the sampling distribution is equal to the mean of the population. The standard deviation of a sample mean, right? Standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of n. So that's why our variability decreases as our n increases, right? Because n is in the denominator. It's the square root of n, so you get, as your n gets bigger, each increase in n has a smaller effect on the standard deviation. But as your n gets bigger, you're dividing by a bigger number, your standard deviation of the sampling distribution is going to be smaller. And when the population is normal, or when n is greater than or equal to 30, the sample mean closely follows a normal distribution. Right? So when we sample without replacement, our selections are not independent, which affects the probability of drawing each successive element of the sample and will change the standard deviation. However, if the sample represents less than 10% of the population, this difference is negligible, which means so small that we're not going to care about it. A manufacturing process is designed to produce bolts with a 0.5-inch diameter. Once each day, a random sample of 36 bolts is selected and the diameter is recorded. If the resulting sample mean is less than 0.49 or greater than 0.51, the process is shut down for adjustment. The standard deviation for diameter is 0.02 inches. What is the probability that the manufacturing line will be shut down unnecessarily? Right? So, our sampling distribution is going to be approximately normal, right? So we have an n greater than or equal to 30. That's our sample size check for applying the central limit theorem. We can also assume that the factory produces more than 360 bolts in a day. Bolts per day. Right? That's going to be our independence check. We check both of those, so we can apply the central limit theorem. And our sampling distribution is going to be approximately normal. If the true mean actually is 0.5, then the mean of the sampling distribution will also be 0.5. So, the probability, so if the true mean is 0.5, we want to find what's the probability of getting something that is less than 0.49 or greater than 0.51. So we want this part of the normal distribution. So we have a normal distribution with a mean of 0.5, and what's the standard deviation? That's the standard deviation for the population. The standard deviation of the sampling distribution is going to be 0.02 over the square root of 36. So 0.02 over 6 is going to be 0.003. So you could now use your calculator to find, using the normal CDF, right, from negative 1E99 to 0.49 with a mean of 0.5 and a standard deviation of 0.003. So this is your lower bound, this is your upper bound, this is your mean, and this is your standard deviation. And then, because your calculator is only going to give you one side of this, we want the other side, we can just straight up multiply this by 2 because they're the same distance away, right? They're both 0.01 away from the mean. If they're not symmetric, you would have to do both of them separately and calculate them and add them together. But here, because they're the same, you do 1 and you just multiply it by 2. And that's going to give us the probability of finding an x-bar in the shutdown range. Right? So, you have to explicitly verify that we can use the normal approximation. So, n is greater than 30, and it is safe to assume the factory produces more than 360 bolts in a day. So here they found the z-score, right? So here's our standard deviation, here's our mean. They found the z-score and then did the normal CDF that way. But you can also, now that we've had more practice with z-scores, you can just do the normal CDF with the 1E99 and then 0.49 and put in your actual mean and actual standard deviation instead of the 0 and 1 that we did previously. And this basically will calculate the z-score for you and then find the probability. So we do that for both of them, or we do it once and multiply by 2, and we get a probability of 0.0024. So, very unlikely that our manufacturing line will be shut down unnecessarily, right? If the actual mean is 0.5, we're very unlikely to get a mean less than 0.49 or greater than 0.51. So, if we do get a mean less than 0.49 or greater than 0.51, we would be pretty confident that this was that there was actually something wrong with the machines, that our true mean was not 0.5. All right, and that's it for that. We'll talk about the difference of two means coming up.